Hello everyone, so welcome to a new video lecture. In this video we begin a new chapter on infinite series and sequences. So we begin with our first section, section 11.1 with Taylor polynomials. So what about Taylor polynomials and how can we connect with something you have done before, in this case something you did back in your Math 121 class in the previous semester, right? In this case linear approximation. So back then you learned that any function, pretty much any function, can be approximated to a linear function around some point x equals a, right? Whatever that is, right? Now, there are other approximations such as quadratic approximations, cubic approximations, quartic approximations, quintic approximations, etc. Right? And we are going to look at these approximations later in the chapters. First of all, we are going to look at one example to refresh on what a linear approximation is. So we have this function, right? F of x equals square root of x, and they're asking us to develop a linear approximation around the point x equals 25. Then we are going to use this approximation to approximate the value of the square root of 26.5. Okay, so linear approximation, in other words, they're asking us for the equation of the tangent line. At same x equals 25. So I'm going to do the calculation first, and then I will show you the visual using graphs so you can have a better overview of what are we doing exactly. Okay, so first of all, to find the tangent line at any point, we need two pieces of information, right? Let's recall that we need the slope and the point. Okay, so well, we are only given the x value of where are we going to find the equation of the tangent line. So we need also the y value. Where are we going to get the y value? By plugging in this 25 in the original function, right? That is the square root of 25, which is 5. Okay, so we are going to have the point p equals 25 comma 5. Now we need to find the slope. Now, how are we going to find the slope? Well, we are going to take the derivative of the function. However, we cannot take the derivative of f of x equals the square root of x just yet, right? So we need to write it with rational exponents and then take the derivatives. And now f prime will be 1/2 times x to the negative 1/2. Right? And if we simplify this, we get 2x to the 1/2 in the denominator, or 1/2 square root of x. So we are going to use this formula to find the slope, right? So f prime evaluated at the value of x, which in this case is 25, it's going to be 1/2 times the square root of 25, which in this case will be 1/2 times 5, which is the square root of 25, and multiplying those two values, we get 1/10. So now we have the point and the slope, the two pieces of information that we need to find the equation of a line. Now, let's use a point slope form. Y minus y1 equals m times x minus x1. So we are going to plug in the values. Y minus equals quantity times x minus, so let's plug in the numbers. So y minus 5 equals the slope, which is 1/10 times x minus 25. Okay, so I know what you're thinking here, right? So you might want to distribute this, right? And then multiply and then get 25 divided by 10. And then we're going to get a bunch of simplifications. Yes, but in this case, let me give you an advice here. In this case, simplifying this expression won't simplify the calculations we want to do for our purpose. You will see why. So in this case, I won't distribute the 1/10. All I'm going to do is add the 5 to both sides to get y by itself. So we do that by plus 5 and plus 5, which cancels minus 5 plus 5. And we get y equals 1/10 times x minus 25 plus 5. Okay, what did we get? Okay, so we got the equation of the line, of the tangent line of the graph f of x equals square root of x at the point x equals 25. So going to our definition of a linear transformation, this means that the square root of x is approximately 1/10 times x minus 25 plus 5, right? Around x equals 25. So they were asking us to use this approximation to evaluate the square root of 26.5. So what are we going to do? We are going to plug in 26.5 wherever we see the x, in this case just here. I think I meant to say 26.5. So, and when we subtract these two numbers, what are we going to get? Okay, this is approximately 1/10 times 26.5 minus 25. That is going to give us 1.5, right? So plus 5, which is approximately, okay, I'm going to change this 1.5 to 3/2 because we are going to need this exact value. So we are going to have 3 divided by 20 plus 5. And if we find an LCD here, okay, keep in mind there is a 1 multiplied by 20, multiplied by 20. The final answer that we are going to get when combining these fractions is 103 over 20. If we use a calculator, right, what are we going to get? I get as a decimal. I didn't evaluate it using my calculator. I thought I did. Let me do that real quick. Okay, so 103 divided by 20, we get 5.15. Again, this is an approximation. Now let's compare with the actual. With the actual value, so the square root of 26.5, put it in the calculator to get 5.14781507. If you round this up to 5, well, I think in this case it's a good approximation, right? This is the actual, this is the approximate value. All right, so let's visualize this on using graphs. Okay, so I have this animation here I did on Desmos. I don't know if you have ever used Desmos before. So and this is helpful to graph function and to also visualize a lot of interesting things. So in this case, I have the graph of y equals the square root of x, and it's a linear approximation, right? And what do I have here? Here I have the the point of tangency, which is highlighted here, 25.5. Okay, the reason why in this case this is a good approximation, that is 26.5, so evaluate this at 26.5, which is around here. Notice in this case the approximation is good because if you look at the tangent line, it's almost on exactly on top of the curve square root of x, y equals square root of x, right? So let's ask ourselves a couple of questions. Number one, can we use this same approximation to evaluate or to estimate, for example, the square root of, I don't know, 66.7? Okay, let me scroll to 66.7. I'm having a hard time. Okay, let's suppose this is 66.7. Okay, so the reason why in this case we wouldn't be able to use this linear approximation, this linear expression to approximate this, because do you see how in this case the tangent line it's off, is way off from the original graph of y equals the square root of x, right? So that's why we wouldn't be able to see this. Okay, let me zoom it out so you can see a better picture, right? Likewise, if we wanted to evaluate the square root of, let's say, 3.3, this wouldn't be a good approximation because see how the tangent line is way off from the original function. So how can we then fix this problem of approximating just any value of a function? Number one, for example, if we wanted to evaluate, let me go back to 66.7, 66.7. So in that case, we would have to find a tangent line at a different point. That is, let's find a number that has a perfect square, right? That is close to 66, in this case 64. That will give us a better approximation. That is one solution. The other solution is to still develop the approximation around x equals 25, but not go only with a linear approximation. So the bigger picture of this section is to add more terms to this linear approximation to obtain a way better approximation. So that is, we are going to use a quadratic approximation, we're going to use a cubic approximation, or a quartic approximation, or a quintic approximation, right? As we add more terms and more terms, you will see how this approximation will be getting closer to the actual function. You will see that in a picture soon as I move on. Okay, so let's define what about those quadratic and cubic and quartic, right? However, let's do another example to do an approximation before looking at the generalized version for this, okay? So worst case scenario on an approximation problem, they would just give you this: approximate 64.3 to the 3/2. That's all they give you. But they don't give you a function, they don't give you the point around which would be a good idea to develop the linear approximation, right? In that case, it would be our job to find that information. So in this case, we are going to guess a function, right? Some function f of x, right? That I would call it x equals x to the 3/2. Okay. How do we know that? Well, because here we have some number raised to the 3/2, so that'll be a good guess of a function. Now, keep in mind that this is the same as saying the square root of x quantity cubed, right? So we would be looking for a number close to 64.3 that has a perfect square to do our linear approximation around that point. And if you're guessing what would be a good number, yes indeed, it would be 64. So in this case, we would do the approximation at x equals 64. Of course, we would need the y value. How do we get the y value? By plugging in the 64 to the 3 halves. In other words, the square root of 64, cube it. Square root of 64 is 8, and cube it, we get this big number, which is 512. Okay, let me write this cube so it looks neat. Okay, there it is. So we have the point. So far we have the point 64, 512. Now we are going to look at the slope, and that's what we need ultimately to get the slope. We take the derivative of the function f prime of x equals 3 halves, x to the 3 halves minus 1 half, that is 1 half. Okay, so let's write it in radical form to simplify our calculations, and we get square root of x in this case. So f prime evaluated at the x value of the point that we want to get to tangent line 4, which is 64. Plug it in here. And this will be 3 halves times the square root of 64. So the square root of 64 is 8. So 3 times 3 halves times, okay, let me erase this real quick. 3 halves times 8, which reduces to 12. So now we have the point P 64, 512, and the slope to be 12. So we are going to use the same form again, y minus y1 equals m times x minus x1, where y1 is the y coordinate of the point that we want to do the tangency point, and m is the slope, which is 12, and x1 is 64. Again, I know what you're thinking here, so you might want to distribute this 12, but my advice is not to distribute, to simplify our calculations and get easier numbers. So this is going to be, let me move over here, y equals 12x x minus 64 plus 512. All right. Now, so they want us to approximate 64.3, but before we do that, here we need to conclude that x to the 3 halves is approximately 12 times x minus 64 plus 512. Only at the point, let's be specific, at the point where x equals 64. Okay, so let's use that expression to approximate the quantity we want to do, to approximate, in this case, 64.3 to the 3 halves. It's approximately 12 times 64.3 minus 64 plus 512. Okay, 64.3 minus 64, that's going to give us 0.3. Which is 3 out of 10. Let's change to fractions, because in this case we're looking for perfect integers first, and then we are going to compare with the actual value. Okay, so we are going to get 36 divided by 10 plus 512 divided by 1, and then find an LCD, multiply, divide by 10 to get approximately, after simplifying this, I get 51/56. Okay, so let's verify. Let's see what we get using the calculator here. So I'm going to divide 51 56 divided by 10, and I get 515.6. Now comparing with the actual value is 64.3 raised to the 3 divided by 2. That's going to give me 515.6042.42155, which is not a bad approximation, right? Not a bad approximation. So I'm not going to do the simulation on decimals. I'll let you do that in your leisure time. So let's see. Now let's look at this generalized form. So when it comes to talking about a quadratic approximation, a cubic approximation, or a quartic approximation, etc., what we are doing is something that in general is called Taylor polynomials, right? So a Taylor polynomial, which is defined using this big expression right here. Yes, it looks big, looks a little bit scary, but we are going to get the hang of it, right? So in other words, what the Taylor polynomial is telling us is that a function f of x, right, and provided that the first and derivatives are defined or exist at the point that we want to do the approximation around. Okay, so the Taylor polynomial, that is a function, whatever function is approximated to all these huge expression, right? Okay, let's look at each part. Okay, so the first two terms we already did. This is the linear approximation. If we use the first three terms, this is a quadratic approximation. Okay, and if we use the first four, we are going to get a cubic approximation, right? And then a quartic and a quintic and so on and so forth, the nth approximation, right? And this is the formula that we are going to use to find those approximations. However, when it comes to looking at these examples, they are not going to ask us to find, oh, look for this quadratic approximation, look for the quintic approximation. Now that is not the vocabulary we're going to use. In fact, like on the first example, they're going to ask us to find P1, which represents the first degree Taylor polynomial, which we learn as a linear approximation, P2, which would be the second degree Taylor polynomial, which in our vocabulary will be the quadratic approximation, and then the third Taylor polynomial, and then the fourth Taylor polynomial, right? So what is the information they will give us? Number one, a function f of x to perform the approximation for, and a point that we are going to do this approximation around. So okay, so let's see what about it, and then we are going to connect the idea with the previous example. Okay, so first of all, we are going to do a bunch of calculations. So we are going to start. So I guess this first example will be boring because we won't see many changes in the numbers, right? So we are going to use f of x first, and then we are going to evaluate the function at the value x, which is in this case represents a, e to the, so this is 0, e to the 0. Any quantity to the 0 is 1. And then take the first derivative. The derivative of e to the x is itself. Evaluate the first derivative at the point. Sorry about that. At the same point, x equals 0. F of 0, e to the 0, that equals 1. Second derivative, e to the x, it's itself. Evaluate the second derivative at the point of tangency in this case. Well, not tangency, you'll see what it's going to call this time. So same thing. E to the 0 is 1. Notice I'm taking continuous derivatives, and again the third derivative. Will I ever stop doing this? Yes, I will stop doing this. How many derivatives are they asking us to take? Well, in this case, they're asking us to find all the way up to the 4th degree polynomial. So we are going to stop at the 4th degree, at the 4th order derivative. Okay. And let's do one more. I know we're getting the same answer, but it is the notation what we need to show in this case. Okay, so this means evaluate the 4th derivative at x equals 0. We get the same result, 1. All right. Okay, so I am going to write number 1. They're asking us to find the first degree polynomial P1. Okay, how are we going to express P1? P1 will be the Taylor expansion using the first two terms. Remember how we highlighted that the linear is going to be the first two terms? It's basically no other than the linear approximation, which we already reviewed on the previous couple pages, right? So in this case, f of a plus f prime of a times x minus a. What is a? Well, in this case is 0, f of 0 plus f prime of 0 times x minus 0. Okay? All right, let's use highlighters just so we can denote where is everything coming from. Okay, I will highlight f of 0 with green, f prime of 0 with purple, f double prime of 0 with yellow, f triple prime with orange, and f fourth derivative evaluated and with blue. Okay, so in this case we are going to use these coefficients. In this case, this will come from the green and this will come from the purple. Okay, so f of 0 is 1 plus f prime of 0, which is 1 also, times x minus 0. But x minus 0 isn't that the same as just x, so that is 1 plus x. So that'll be the first polynomial. Okay. Now, let's look for P2. P2, which is the second degree polynomial. That'll be f of a plus f prime of a times x minus a plus f double prime divided f double prime of a divided by 2 factorial times x minus a to the second power. In this case, we stop there. Let's check with our generalized form for quadratic, the one we highlighted in green. That is the first 3 terms. Those are the terms that we are using. Okay, so let's plug in numbers to this. So what did we say about f of a? Well, in this case, I will keep writing every single symbol just so you can still keep track of what is a and where is it coming from. Later on I won't write the a anymore. I'm just going to write whatever the point we are doing the expansion around. Like in this case it's 0, but this time I will just do it just so you can follow and you can keep track of everything. So p2 p sub 2 of x equals f of 0 plus f prime of 0, no, not of 0, yes, f prime of 0 times x minus 0 plus f double prime of 0 times x minus 0 quantity squared. Don't forget to divide by 2 factorial. Okay, so again, color coding. We said f of 0 was the quantity in green. F prime of 0 is the quantity in purple. And what about the double prime? That's yellow. And what are those quantities? For all of them, again, they are just 1, right? So I'm going to just write 1 plus 1 times x minus 0 plus 1 over 2 factorial, which is 2 times x minus 0 quantity squared. Okay, in this case, we can reduce this to just 1 plus x plus 1/2 x squared. So that is our final answer. Let's go over P3. P3 will be, I'm going to write all the generic formula first. So f of a plus f prime of a times x minus a plus f double prime evaluated at a divided by 2 factorial times x minus 0 squared plus f triple prime evaluated at a, f of a rather, it's divided by 3 factorial. In this case, we are going to go with the third degree polynomial. Okay, what about this exclamation sign you see? This, I mentioned it, but I didn't explain what it was. We're going to go over this factorial symbol later when we cover power series, which is related to Taylor expansions and Taylor polynomials. But essentially, when we look at n factorial, let me just briefly do it just on the side. This exclamation sign, for example, 4 factorial. This is not an excited number like 4. Whoa, no, that's not what it is. This means the multiplication of the number that we have the factorial 4 times the previous one times this previous one, and all the way when we get to 1. So 4 times 3 times 2 times 1, that's 4 times 3, that's 12 times 2 times 1, and then this is 24. Okay. Likewise, 3 factorial will be 3 times 2 times 1, which is 6. Okay, so let's see. F of 0 plus f prime of 0 plus x times x minus 0 plus f double prime of 0 divided by 2 factorial, which is 2 times x minus 0 squared plus f3 triple prime evaluated at 0 divided by 3 factorial, which we already said it's 6 times x minus 0 cubed. So what is this going to be? This will be 1 plus 1 times x minus 0 plus 1/2 times x minus 0 squared plus 1/6 times x minus 0 cubed. Okay, let me clean this up. Let me clean up the zeros. I'm just going to write 1 plus x plus 1/2 x squared plus 1/6 x cubed. Okay, and that is the third degree Taylor polynomial for the function e to the x around x equals 0. Last but not least, let me do the same before of x, and to save some time, I think I'm just going to copy this. It is easy for you to write it with a pencil on paper. It is harder for me to write here in this tablet. So in this case, we're going to have this approximation. And whoops, let me erase this little part right here. This will be P4. And let me add one term plus the fourth derivative evaluated at a over 4 factorial, which we already said it was 24, times x minus a to the 4th power. All right, before of x will be f of a, which is f of 0 plus f prime of 0 times x minus 0 plus f double prime evaluated at 0, which is a, divided by 2 factorial, which is 2, times x minus a squared plus f triple prime of a divided by 3 factorial, which I'm not going to write it in terms of factorial, that's a 6, and times x minus 0 cubed plus one more term, essentially the same terms as before, and we add only the 4th term, in this case f of f quadruple prime at 0 divided by 4 factorial, which is 24, and this will give us, times x minus 0 to the 4th power. So the first 1, 2, 3, 4 terms are exactly the same polynomial I wrote before. This will be 1 plus x plus 1/2 x squared plus 1/6 x cubed, and this will be the fourth derivative evaluated at 0, which will be also a 1 over 24. And x minus 0 is just x to the 4th power. All right. Okay, let's visualize this with graphs. Actually, this is the exact same example from our textbook. Okay, so we have 4 graphs here. Number 1, this first graph represents P1, which is y equals 1 plus x. Do you see in this case it's a linear equation, right? It's a linear equation, and it's tangent to the point 0, 1. P2 is this function that we have here. Now let's compare P1 with P2. All right. Did you see how this approximation is good for just a few points right here? Maybe this graph overlaps just a few points around in the neighborhood about the point of tangency, right? Now, if you compare with P2, the approximation covers more points on the graph of the original function. Let's look at the third degree polynomial. In this case, P3 equals this function. And in this case, see how as we increase more terms, we get closer and closer to the actual function, right? So Now let's look at P4. Finally, see how P4 is basically, but not quite, because it covers way more points. And it approximates e to the x at more points rather than its original P1, the baby linear approximation that we learned in Math 121 in the first semester calculus, and we are now extending this idea to larger polynomials for a better approximation. So again, going back to the graph that we have on Desmos. So I guess that if we keep adding more terms, well, not that I guess, it's actually a fact. If we add more terms, if we graph the quadratic or the quartic or the quintic, this won't be a line anymore, and it will be getting closer and closer to the graph of the radical function rather than still being a line, and it will be useful to do better approximations. And here is a picture, the one from the example in our textbook. Let's do another example. Example 4. Obtain the second Taylor polynomial of f of x equals square root of x at x equals 25. Then use it to approximate the value of 26.5. So basically, the first example we started on in this section, but now we are going to obtain not only the linear approximation, in this case which would be P1. In this case they're asking us to do P2, and no, we're not going to do one at a time. So in this case we are going to go straight to P2. They're not telling us obtain P1 and P2. They're asking us straight to P2. The previous example, we developed P1, P2, P3, and P4 to compare every single case by overlapping the two graphs for every single case and see how the approximation every time gets better to the actual function. So now let's get this done. So again, the y value for this from our first example was 5, I believe. So let's see. So f of x equals not square root of x, but x to the 1/2. And then we are going to take the derivative, evaluate this at f of 5. Okay, I know I already got it here. Let me do it again just to follow the same procedure as I did on the previous example. This is 5. And then f prime evaluated, it's f prime of x is 1/2 x to the negative 1/2, which equals 1/2 square root of x. That's what we got from the previous example, from our first example. Now we are going to evaluate the first derivative at x equals 25. We already did it. Let's do it again. 25, 25. This will be 2 times 5 in the denominator. That's 1/10. Let's take f double prime. So multiply negative 1/2 times 1/2. This is going to give us negative 1/4 x to the negative 3/2, which in this case, first of all, we need to work a little bit with exponents and radicals. So negative 4x to the 3/2 in the denominator and equals to negative 4 square root of x quantity cubed. So now we are going to evaluate this second derivative at 25. And when we simplify this, the square root of 25 is 5 inside. 5 cubed then is 125, and then that 125 times 4, that's going to give us negative 1 over 125. Okay, so these are going to be our coefficients. Okay, let me make this a little bit more presentable. I think there's a lot of space in between. And just give me 1 second here. Sometimes I just write too fast that I leave a lot of. Okay, let me leave it here. Okay, so this will be the coefficient of the first coefficient. This will be the second coefficient, and this will be the third coefficient. Okay, so in this case, I'm not going to do P1 and then P2. I'm going to go straight to P2. So P2 will be, and in this case, well, f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus a squared. So in this case, a is no longer 0 like in the previous case. Okay, so in this case, a equals 25. So I'm going to write f of 25 plus f prime, just prime, of 25 times x minus 25 plus f double prime of 25 divided by 2 factorial, which is 2, times x minus 25 quantity squared. Okay, so color coding, f of 25 is 5, f prime of 25 will be this quantity 1/10, and then f double prime evaluated at 25 is this quantity negative 125. So let's plug in the numbers, and we're almost done. Actually, it's not going to take as long as the previous example. So I got 5 plus 1/10 times x minus 25 plus negative 125 divided by 2 times x minus 25 quantity squared, which simplifies to 5 plus 1/10 times x minus 25, and in this case minus 1 over 250 times x minus 25 quantity squared. So this is P2 of x, P2 of x, P2 of x. Okay. Now they're asking us to use this expression, this function, to approximate the same quantity. The square root of 26.5. Okay. So in this case, p sub 2 of 26.5 . So this will be 5 plus 1/10 times 26.5 minus 25 minus 1 over 250 times By the way, this is supposed to be with blue. Negative 25 squared, that is 26. 26.5 minus 25. When simplifying this quantity, we get 5 plus 1/10 times, what did we get? 1.5 minus 250 under 1 times 1.5 quantity squared. So I'm not going to leave anything using decimals. I'm going to change everything to fractions. So 5 plus 1/10 times 3/2 minus 1 over 250 times 3/2 quantity squared, which reduces to 5 plus 3 over 20. You might recognize these numbers from the previous example, from our very first example actually, because those are from the linear approximation. All we are doing now is adding the second term. I didn't want to just copy and paste what we had from the linear approximation, because otherwise you wouldn't see the concept of what we are doing for this case. So we are multiply, that's going to be 9/4. Okay, the next is just arithmetics. 5 over 1 plus 3 over 20 minus 9 over 1,000. Okay, so let's find an LCD. Multiply by 1,000, by 1,000, multiply by 200, actually by 4,000, because this is going to be, wait a minute, where did I get looks like I got something weird. Okay, let me go back. This is supposed to be not 125, by the way. This is supposed to be 1 over 500. So this is, let me erase these little mistakes here. $500, and this will turn into 1,000. No wonder I was getting numbers that I weren't familiar with. And then 1,000, and then 1,000, and finally one more 1,000. Okay, so this will be 4,000. Okay, and this will be times 200 here to give us a 4,000. So if we combine all these numbers, we should get 20,591 divided by 4,000, which using decimals we get 5.14775, which again, comparing with our calculator value from our first example, 5.147815, 5.147815, was it, or what was it? 781507. The actual. So highlight the approximated value, highlight the actual one, and let's compare with the one we got from the linear approximation, 5.15. Okay, so we got P1 of 26.5, 5.15. P2 of 26.5 is this number we have here, 5.14775. See how this adds more digits to the decimal places, getting even closer to the actual value. So that's another example in which we use better approximation to obtain more accurate results when evaluating these functions. And just to wrap up this section, let's do one Taylor polynomial that has to do with trigonometric functions. And this one is going to be fun. This one is going to be fun to write. So this will be the fifth Taylor polynomial. So in this case, they're asking us to go straight to P5, not to develop P1 and then P2 and then P3 and then P4. No, unless they say it on the instructions to obtain P1, comma, P2, comma, etc. as you will see on the textbook exercises. Well, in that case, you will have to show every single one of them and then compare with the graphs of the actual function, like we did with the exponential case. Okay, so number one, well, I didn't mention on the previous examples, but the function has nth derivatives and it's defined at the given value of x, as we were able to see. So number one, f of x equals sine of x. So we evaluate the function at pi over 3. Okay, so let's evaluate pi over 3, pi over 3. Okay, if I like using the triangle, so I'm just gonna go, so this will be the square root of 3, 1, and 2 to find the trigonometric value. So sine, which is opposite over hypotenuse, this will be square root of 3 over 2. Take the first derivative of x. Sine x. No, not sine. Hold on. Cosine. I was just copying, I guess. I had an extra parenthesis. Cosine x. And then evaluate the second derivative. The first derivative at pi over 3. So in this case, cosine of pi over 3 is adjacent over hypotenuse, that is 1/2. The second derivative of x is negative sine. The derivative of cosine is negative sine of x. Evaluate the second derivative, which is negative sine, at pi over 3. But again, sine pi over 3, we already had it. Did you notice that? But in this case, we are going to get just the negative square root of 3 over 2. The third derivative, f triple prime of x equals negative cosine of x. That is, okay, give me a second here. And arrow f triple prime evaluated at pi over 3, pi over 3, pi over 3. So this will be negative 1/2. The fourth derivative will be the derivative of negative cosine. Okay, the derivative of cosine is negative sine times the negative that we have here will turn into sine. So evaluate sine at pi over 3 okay, I don't know what's going on here. Give me a sec. Oh, there it is. So pi over 3. Okay, I don't know what happened here. It turned like a little bit larger. Okay, there it is. Something happened. Okay, it's fixed now. So pi over 3, sine of pi over 3, square root of 3 over 2. See how the values cycle back? Remember that exam question? How the derivatives of sine cycle back after the fourth derivative or any multiple of 4 order derivative. And finally, we do the fifth derivative of x. Oops, silly mistake again. That's cosine x f cosine pi over 3. It's going to be 1/2. Again, I don't know why it doesn't let me change the color. Okay, pi over 3, pi over 3. Okay, so we have the coefficients of f prime, f double prime, f triple prime, f quadruple prime, f quintuple prime. All right, this one is going to be a fun one to write. Okay, so P5, and you might want to write tiny in this case, a little bit tiny. So P5, let me write down all the terms. P5 will be f of a plus f prime of a times x minus a plus f double prime of a times x minus a to the second power divided by 2 factorial plus f triple prime of a times x minus a to the third power divided by 3 factorial plus f quadruple prime evaluated at a divided by 4 factorial plus times x minus a to the fourth power plus f quintuple prime evaluated at a divided by 5 factorial times x minus a to the fifth power. Okay, so that's what we are going to use. Okay, so P5 of x will be, first of all, f of a, which in this case is f evaluated at pi over 3. This will be the square root of 3 plus the first derivative evaluated at a, which in this case is this guy right here, 1/2, times x minus a, which in this case pi over 3, plus the second derivative evaluated at the same value of a, which is pi over 3. We get negative square root of 3 divided by 2, negative square root of 3 over 2, divided by the quantity 2 factorial, which we said it was 2, times x minus pi over 3 squared, plus, okay, I think I'm going to run out of colors here. Okay, so blue, blue for the third derivative. Evaluated, we get 1/2. So negative 1/2 divided by the quantity 3 factorial, which we said on the previous example, it was 6. Okay, let me start making some space here. And that times x minus pi over 3 to the third power. Let's go with the 4th-degree polynomial plus, okay, orange in this case, the 4th derivative evaluated at pi over 3, square root of 3 over 2 again, positive, square root of 3 over 2, divided by 4 factorial, which we said it was 24, times x minus pi over 3 to the 4th power, plus finally the last derivative in this case. Okay, let me use yellow again. This one right here, that's 1/2. That's 1/2 divided by the quantity 5 factorial, which in this case 5 factorial multiply 5 times 4, which is 20. 20 times 3 is 60 times 2, which is 120. Times x minus pi over 3 to the 5th power. So we're done writing the polynomial, right? Let's just simplify the numbers right here. So p sub 5 of x equals square root of 3 over 2. I forgot a division by 2 here. Square root of 3 over 2 plus 1/2 x minus pi over 3 plus multiply 2 times 2 to get 4. In this case, it's actually minus square root of 3 over 4 x minus pi over 3 quantity squared plus multiply 2 times 6, that's a 12, that's actually a minus again. X minus pi over 3 cubed plus multiply 2 times 24, that's 48, square root of 3 over 48 times x minus pi over 3 to the 4th power plus 120 times 2, that's 240, 1 over 240 times x minus pi over 3 to the 5th power. So that is our final answer to this exercise. I hope you see the pattern here. If you look at the bigger picture, all we are doing is just taking derivatives and evaluating at the point that we want to do the approximation around. The rest of it is a lot of writing. It's kind of tedious to write every single step sometimes, but again, be sure to write everything down when solving a problem like this. There's no way you can do, I guess, this by just doing in your head. So you need to show all these derivatives, all this work, so you can show this in the best organized fashion, right? So this is the end of the section. So I will see you on the next video in which we introduce infinite sequences. Okay, see you then.